feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instructional lesson here with Mr. Gaines as we start a new unit talking about systems of equations. Today we are going to focus on linear systems in two variables and kind of establish a background for what a system of equation is. So let's go ahead and jump right into the content. Systems of equations you may be familiar with from Algebra 1, but let's go ahead and start with a definition. So a system of equations would be a set of two or potentially more equations that share common variables where you're trying to find a solution that works for both or all three or all four equations. So you're looking for one solution that satisfies all equations in the system. To kind of get a better idea of that, we're going to consider kind of a word problem, an application problem to start and see how we can create a system of equations. So in problem number 1, it says, consider an amusement park that brought in $3,100 in revenue by charging $9 for adults and $5 for children while selling 500 tickets. So in part A, it says that we want to use A for the number of adult tickets sold and C for the number of children's tickets sold. And in doing so, write an equation to model the total number of tickets. So total number of tickets would be the number of adults tickets, A, plus the number of children tickets, C. And we know that they sold a total of 500 tickets. So A plus C has to equal 500. In B, it says using the same variables, write an equation for revenue generated by sales. Remember that, as we've seen earlier this year, revenue is equal to sales times price. So our total revenue would be the $3,100 that they generated. Now they charged $9 for adults and $5 for children. So revenue from adults would be $9 per adult ticket. So 9 times A. The sales would be A, the price would be 9. We're going to add to that the revenue generated by the children, which would be $5 per ticket times the number of children's tickets sold. Together, these values have to equal $3,100. So it says in part C to write an expression to show that equations from both A and B are being considered simultaneously. I have a little typo there. So generally how we write a system of equations is we kind of put them together with this notation that tells us that we're going to be combining these two equations together into a single system looking for an answer to both of them. So I have an equation from A, an equation for B, and together they are a system. In D, it says to verify that 150, 350 is a solution for the system of equations. So we're going to assume right now, it didn't really tell us, but we're going to assume that A is 150 and C is 350. So I want to verify for both equations. So I'm going to take these values and substitute it into both equations. So if I substitute in 150 for A, I get 150. And substitute in 350 for C, I would get 350. And this value does equal 500. So if I started with, let's rewrite this. If I started with A plus C equals 500 and substituted in 150 and 350 for A and C, I'd get 500 equals 500. So that is, it is going to satisfy the first equation. Now let me do the second equation. 9A plus 5C equals 3,100. So let me take 9 times 150 plus 5 times 350. And see if that's going to equal 3,100. And we can go ahead and head over to the calculator here. If needed, 9 times 150 plus 5 times 350 is 3,100. So this would be a solution to our system. So we were given kind of the answer already that 150 adults tickets and 350 children tickets were sold. But through substitution, we can verify that these two answers are, or these two values are answers for our system of equations that we created in C. So C would be a linear system in two variables, which is what we're focused on. Now, we're not always given the answer outright. We're most commonly looking for an answer. There's a few different ways that we're going to approach finding solutions. The first way we're going to take a look at is graphically. Now, we're not always going to be able to use a graph to find solutions, but when we can, it's probably faster and a little bit easier to use the technology. It's also going to be a route for us to check our answers as we go through. So if we look at problem 2, it says solve each of the following systems by graphing, round to 2 decimals as needed. So we're going to round to the hundredths place. You may look at 2a and notice that these are both linear equations because they include an x to the first power and a y to the first power. Our most basic equations that we've dealt with this year. In order to graph them using our graphing calculator, which we'll have as a resource or assistance on our tests and quizzes, we need the equation to be written in slope-intercept form, in the form y equals mx plus b. So what I'm going to do is I'm going to take these equations and I'm going to rewrite them into the form y equals mx plus b. So if I take the first equation, 4x minus 3y equals 9, I would need to subtract 4x from both sides. So I'd have negative 3y equals negative 4x plus 9. Then I would divide negative 3 from both sides. So I'd have negative 4 over negative 3, which is just 4 over 3. And 9 divided by negative 3, which would be negative 3. So this is my first equation in my system. I'm going to go ahead and rewrite my system down below here in a little bit. My second equation, I'd complete the same process. 2x plus y equals negative 5. So here, a little bit easier of a rewrite. Just add 2x to both sides, and I get 2x minus 5. So another way to write my system of equations would be y equals 4/3 x minus 3, and y equals 2x minus 5. So the reason, again, that I wrote my system in this manner is because now I can graph. So if I put 4/3 x minus 3, and I put 2x minus 5 into my calculator, and I hit the graph key, I'm going to make sure I'm in the standard window for right now, it's going to graph my lines. So the first line that was drawn here, this was the first line. This is showing us all possible values that would be solutions to the equation y equals 4/3 x minus 3. So if I were to look at my table, like 3 and 1 would be a solution to that equation. 0 and negative 3 would be a solution to that equation, and so on and so forth. The graph of this second line showed us all the solutions to 2x minus 5. What we're looking for is common solutions. Both of these are lines, and so we know that from geometry that when we have two lines on a Euclidean plane or on a flat surface, they're going to intersect exactly one time, and we can find that intersection right here. So using our graphing calculator, we can use the calculate menu, so hit second and trace to find intersection, the fifth option. When we select that, it's going to say first curve, so I'm going to make sure my cursor here, my blinking cursor, is on one of my two lines, hit enter. It's going to say second curve, I want to make sure it's on the second line, and it is, hit enter. I don't really need to guess, I'm just going to hit enter, and it's going to find the intersection. So the solution for this system of equations, we can write the solution a few different ways. The solution would be x equals 3, y equals 1. So this is one way we can write the solution. We could also write the solution as a coordinate pair, 3, 1. And there we had the solution. So if I wanted to, I could check by substituting. I could take 3 and 1 and put it back into my original equation here. So this would be 12 minus 3 equals 9. So it is a solution for my first equation. I could take 3 and 1 and put it back into my second equation, which would give me negative 6 plus 1, which equals negative 5. So this solution satisfies both equations. Let's take a look at B. Actually, if you kind of get the concept here, pause the video and see if you can complete B. Hopefully you got a chance to work through B. Let's go ahead and work through it together. So the first thing that I want to do here is I want to rewrite my equations into slope-intercept form. So for my first equation, it's a pretty easy rewrite. I'm going to subtract 3x from both sides. So I would have negative 3x plus 2. So that is from the top equation that was listed there. The second equation is a couple more steps. So I'm going to subtract 5x from both sides. So I'd have 3y equals negative 5x plus 12. And then I'm going to divide by 3. So y equals negative 5/3 x plus 4. So I can write this as a new system. So my new system would be y equals negative 3x plus 2. This is equivalent to the previously one that I wrote, but just written in a little bit of a different format. Now I can graph the two equations. So I'm going to go into my calculator, and I'm going to type in the equations as I have them written. Y equals negative 3x plus 2, and y equals negative 5/3 x, or 5 divided by 3x, plus 4. Going to go ahead and take a look at the graph here. I'm looking for a single intersection, and I can see that intersection kind of up here in quadrant 2. I can find that by hitting second, trace, in the calculate menu going down to the 5th option. When it says first curve, making sure my blinking cursor is on one of the two lines, hitting enter. Making sure on second curve it's on the other of the two lines, hit enter. I'm not going to guess, just hit enter. And there we have our answer. So our answer could be either written as x equals negative 1.5, y equals 6.5, or it could be written as a coordinate pair, negative 1.5, 6.5. Again, we could check that. So if I substituted in, negative 1.5 times 3 is negative 4.5, plus 6.5 would be 2. If I substitute negative 1.5 in for 5, that is negative 7.5. If I substitute in 6.5 for for y, 3 times 6.5 is 19.5. 19.5 minus 7.5 would be 12. So this is this point is the solution to both equations in our system. So this is kind of an overview of linear systems of equations, just dealing with two variables and how we can solve them graphically. This is a good place to stop for today. So as we move a little bit further, we're going to take a look at algebraic examples of how to solve systems of equations. As always, thank you guys for tuning in, and we'll see you soon.